In this video, we'll be learning how to compute line integrals. So in the previous video, we talked a lot about the theory behind it, but we didn't actually compute any. So let's compute some right now and see how it's done. So this is pretty much a step-by-step process. So here's the integral we want to compute. We want to compute the line integral of modulus z squared on the curve gamma. And the curve gamma is a line segment from 2 to 3 plus I. So the first step always is to draw your curve. Even if you don't think you have to, just draw it. It'll help you. So here's 2, here's 3 plus I. And the line segment is like this. And it has a direction, which is, we know the direction because it's from 2 to 3 plus I. And this is our gamma. Okay, so the next step is to parameterize this. We need to get an explicit formula for it. So remember we talked about how to do this for line segments. Gamma of t equals the starting point plus something times t. And the something is the difference between the ending point and the starting point. So 3 plus I minus 2 is 1 plus I. And now we have to also give the range for t, which is 0 to 1. So quick check, this works, right? Because if we plug in 0 for t, we get 2. If we plug in 1, we get 3 plus I. So this will work. Now, the other thing we learned about line integrals is that this is equivalent to the limits of t, 0 to 1, and we put in the function. So the function in this case is v of z equals modulus z squared. So we want to put in v of gamma of t into here. So that's going to be, we put gamma of t in here. This is going to be 2 plus 1 plus I times t. And I'm going to rearrange this a little bit so I can get real and imaginary parts. So I'm going to write this as 2 plus t plus it. Okay, so that's because I want this real part and this imaginary part. It'll help because there's a modulus involved. So now I'm going to write the modulus of this squared. So what is the modulus of this gamma right here? So it's going to be radical 2 plus t squared plus t squared. And I square that, so the square root goes away. So it's just going to be the inside part, and when I expand this, it's going to be 4 plus 4t plus t squared plus t squared. So it's going to be, in all, it's going to be 4 plus 4t plus 2t squared. 4 plus 4t plus 2t squared. And remember, we need to multiply this by gamma prime. So we need to take gamma prime of t equals, and this is why I split it into two components. So it's going to be 1 plus I. 1 plus I. So 1 plus I dt. And the reason I'm able to write it like this, so go back to the previous video on the theory over line integrals if you want a quick refresher on why I'm allowed to do this. But we talked about how you can transform a line integral into something that just involves t, something that's much easier for us to compute. So the form is, again, limits of t. You take the function and you plug in the gamma, you write gamma prime, and then dt. So now this, no piece of cake, we can evaluate it. So this 1 plus I is just a constant. We can take it to the outside. And we're going to evaluate this inside integral. It's going to be 4t plus 2t squared plus 2/3 t cubed, limits 0 to 1. So we plug in 1 into all this, we get 4 plus 2 plus 2/3 is 6 plus 2/3 is what? 20/3. And don't forget the 1 plus I we had taken outside, so this is 20/3 1 plus I. That is the value of the line integral. So just to recap, the process is always draw a graph, always draw a graph, parameterize the curve in explicit formula, and then just plug everything in the equation after you take the derivative and stuff like that, and then work it out using your normal calculus techniques. We'll do one more here on the back, so to get a different curve. This is going to be, we want the line integral of z squared on the curve gamma, and the curve gamma will be the semicircle from 1 to negative 1 through I. So remember, always first draw the graph. Here's 1, here's negative 1, and the semicircle through I. So here's I. So the semicircle is going to look like this. And what's the direction of travel? Well, it says from 1 to negative 1. So the direction of travel is this way. Okay, so next step is to parameterize this. What's the gamma formula? Remember we said for circle, it's going to be radius. So I'm going to write the 1, even though I don't really have to. 1 times e to the I t, and that's the formula. And t's range, we have to be careful here, because in the previous video we talked about the range being from 0 to 2 pi, but that's if we want the full circle. Since we stop at the halfway mark, this starts at 0 and it goes to the angle pi. So t's range is 0 to pi. Okay, you got to be careful with your ranges, be careful with your parameterization. This is actually the hardest part. Once you figure that out, you know it's good. Then you just do calculus techniques. It should be good from there. So now let's write the integral in the form we have. Integral. So limits now of t, and then what's the function? The function is z squared. So I want to take the gamma and square it. So it's going to be e to the 2it, e to the 2it, and now I want to take gamma prime. So gamma prime of t is going to be, I'm going to take the I down, so it's going to be IE to the IT. Okay, so you just treat I like a constant when you take integrals, derivatives, stuff like that. So now we plug that in here. I'm going to take the I outside because it's a constant, and we're going to have e to the IT dt. So now these two can multiply together. So I 0 pi e to the 3it dt. Now this we can work out. So it's going to be I times 1 over 3i e to the 3it limits 0 to pi. Okay, so let's work this out. This I and this I can cancel, so it's just going to be really 1/3. And it's going to be e to the 3 I pi minus e to the 0. E to the 0 we know is 1, so it's going to be 1/3. E to the 3 pi I minus 1. So what is e to the 3 pi I? From the exponential video, we know we can write this thing as cosine 3 pi plus I sine 3 pi. Sine 3 pi is 0, cosine 3 pi is negative 1, so this is going to be negative 1 minus 1 times 1/3. It's going to be negative 2/3. So interesting, this has no imaginary component, but our answer on the back did have an imaginary component. So you see, this is really not that hard to work out. You just got to be very careful in 2 steps. The first thing is drawing the graph. Make sure you understand what the gamma is. The second thing is writing the parameterization. If you have to, look at it, plug in different t values, and make sure it works. But once you have these 2 things solid, you're good. Then you just put everything in the form that we had in the previous video, and then you just work through, and you should get a nice answer in the end. Okay?